think he's probably got to start it. So it says, he'll let you know though if it's not, I can stop. Yeah, he mutes it and turns it on. Okay, I think we can get started. Is the audio working back there now? Okay. Well, welcome everybody, and thank you for coming to the 2022 George Pack Graduate Student Awards Symposium. So it's actually for the year of 2021 to 22. So we're giving out the award for that, and we're going to give out some graduate awards here as well, and then of course end with the Pack Award, and then have a presentation from our awardee. So, but first before we get started, I'd like to introduce the Associate Dean of Research, Dr. Michael Menz. Thank you.
Thank you, everybody. It's a great pleasure to be here today. And I want to take this moment to actually congratulate all of you who have achieved an enormous task. You were able to do your hard work, to the days that you spend in the lab for long hours, to actually receive the highest degree possible in your career. However, considering that you are now certified to be able to create new knowledge. You had moments at your lab bench where you discovered a certain principle, where you enlightened a hypothesis or falsified or verified that hypothesis. So there were moments in your life where you were the only one who knew this little piece of knowledge. Nobody else in the world knew what you just discovered. How cool is that? However, also keep in mind, with being able to create knowledge comes a lot of responsibility. Nearly 100 years ago, T.S. Eliot said, "Where's the wisdom that we lost in knowledge? Where's the knowledge that we lost in information?" And nowadays we can probably add to it, where's the information that we lost in data? So I hope that first, after all, you celebrate the great achievement that you have accomplished here. But I also encourage you to be responsible and try to use or take ownership of the knowledge that you produce and make sure that it's used with wisdom. You went through an enormous phase of changes. And when we are looking at human history, currently the rate at which change occurs to which you have to adapt is faster than it was at any point in human history. So knowledge is generated at a faster pace. Societal challenges occur at a faster pace. However, I can assure you, the rate of change currently is the slowest rate that you will experience for the rest of your life. It will only get faster and faster. That means you need to be able to advocate for the right change, to be able to enforce that the knowledge that you are producing is used wisely. Thank you very much.
Okay, so before we get to the awards, I just like to say a few words about Professor George Pack, our previous chair in our department, just to kind of remember him, since the award's named after him. So he got his PhD in 1973 from SUNY Buffalo. Then he did postdocs at University of Rochester, NYU, and Stanford. He then became a professor of biophysics in 1978 at the University of Illinois Chicago in the College of Medicine. So there he was a theoretical physical chemist, studied a little bit on enzymes, but mainly DNA, RNA, dynamics of DNA and RNA, and how electrolytes and ions interact with them and alter conformations. He worked with other large molecules like polyelectrolytes. But what's interesting is he also worked a lot with mice cells, and he looked at the structure of mice cells and how ions interacted with mice cells and made those calculations. And today's speaker will also be talking about mice cells. So there's a nice connection there with you, Eric, and Dr. Pack. So that makes this year particularly special. But lucky for us, in 1998, he came to the University of Louisville, where he transitioned from, he still was an active researcher, but also took a leadership role, obviously, in our department as chair. And really, I remember in the early years that I was here, he always spoke about, wanting to do something on a bigger scale and really lead a entire department rather than just a research group, and have a bigger effect on not only the faculty, but the entire university, and especially graduate students and more graduate students. So he was able to do that from 1998 to, up till 2010. He hired 19 faculty here. And he always said, Frank, we want to hire great scientists here, but we don't, well, I won't say the word, but we don't want any basically jerks here. So you can see what kind of person he was. He was really, and that actually established a great culture, I think, in our department, which we still see today. It's very collegial. We get along very, very well, I think, for a chemistry department where, it can be very argumentative and combative, but, that was something he really took pride in with this department. We awarded 58 PhDs while he was here. He also became Associate VP of Research and Innovation in the Executive Vice President of Research's office. And then he took both of those roles from 2007 to 2010. He was both chair and associate VP of Research and Innovation, and did that and then he actually just did the Vice President of Research for up until 2013. So overall, I just want to say he's a really great guy. As I said, you can see how he established a really great culture here. He was always at the seminars, so he definitely would have been here. He went to every seminar. He sat kind of right up in front here with his bow tie on all the time. He took the speakers out all the time. One of the speakers I had here, he actually took him to an opera. So it kind of shows you what kind of person he was. He took him to the Barber of Seville. That speaker still tells me that was one of his best visits, that he's ever had. So, he's always here at always at the Christmas parties. He went to basketball games, football games, hung out with the faculty. Was always present. So he just walked through the halls, a lot like Sachin does now. So he'd walk through the halls, just stop in your office and talk to you. At his 60th birthday party, my wife actually brought an Over the Hill sign and put it in his front yard, and I hadn't had tenure yet. And he goes, Frank, there's no way you're getting tenure now. I mean, you're done for. So he also fought for diversity. I think we were over 25% female in our department during his time here, and he was very proud of that. So I think that was another important thing he really strove for. He increased the research productivity in the department. I think there's no doubt about that if you look at the funding levels and then the number of tenure-track faculty we had after he hired assistant professors. I was lucky to be hired by him. He hired senior faculty like Eugene and GB. And Nance. So we were really lucky, kind of covered all areas and really grew the department. And then if you get to graduate students, he really knew the importance of graduate students as well. So he would love that this award, awards named after him. So he always supported them and fought hard for growing the department and actually, affecting more graduate students. The only other thing I can say is that, just through this award, I think he's, still affecting graduate students. Hopefully this award is something on the younger graduate students' radar that you achieve you strive for, and that you have a goal to achieve one day. And through that, George will keep improving our department. So with that, I think, that's all I would like to say about George. It's an honor to speak here about him and have this award on his behalf. And of course, I want to thank the family for coming. This award wouldn't be anything as nearly what it is without your guys' participation. So we have Tom and Jerry here today, and then we have Choo Choo and Barbara, and then Choo Choo's daughter Faith. So thank you for always attending this every year, and I'd like to give you guys a round of applause for that. Okay, so actually last year we expanded this. We used to just give the George Pack Award and just give one award. And this is the 10th award, so the anniversary of 10 here. We started in 2014. We gave out 2 one year, so this is why this is the 10th. But we now expanded to have other awards, so we can actually expand the effect of this event and actually, cover more than one student award. So I would like to present the first award to Johan Hemmer. So this is the Director of Graduate Studies Award, and actually our Director of Graduate Studies, Lee Thompson, he's on sabbatical, otherwise he'd be here doing this. But this is he's from England, so he calls this the award for most auspicious first years. Come on up here, Johan. Maybe we can all take a picture.
How do we do that?
Thank you.
Maybe I'll take a picture here, Johan. You can go in the middle. Congratulations.
You hand them out, I shake hand.
Sure, okay, let's do that. All right, if I mess up any names, forgive me. So this is, again, a Director of Graduate Studies Award for Character and Endeavor. This is Sahar Miragahi? Miragi? Congratulations. Okay, this is a Graduate Teaching Assistant Award, so a lot of our graduate students get funded by being a teaching assistant in our labs and our lectures. This is for recitation, so this is the best recitation graduate teaching assistant to Adam Kinyua. Adam here. Congratulations. Okay, this is for the also Graduate Teaching Assistant Award, but for laboratory work, and this goes to Mohan Patel. Big surprise.
Thank you very much.
Actually, Mohan, you can stay up here. Mohan also is the recipient of the Dorothy Gibson Award, which is a fellowship we award to graduate students in honor of the late Dorothy Gibson, who was a professor of organic chemistry here. So, congratulations, the Dorothy Gibson Award.
Thank you again. Oh, again?
Yeah, you get two pictures with us.
Thank you.
Okay, we have another endowed fellowship that's also for a graduate fellowship through, it's called the Arnold Spatola Award. Again, another professor of organic chemistry. And this one goes to Ramisa Mohammed. Congratulations. Okay, I guess
Which way?
Okay, and then maybe I'll have, before we do the final, do we want to do the award before, or you want to, you just introduce when we do the seminar. So we'll have Thayer come up for the, to receive the George Pack Award, the big one. Maybe we can have the family come up and take a picture with this one, or, oh, we do one here first. You want to go over here maybe for that? Sashin, if you can come up too.
I will sneak out.
What's that?
I will sneak out.
You want to get one more picture in here? You can get
Oh,
on
sure,
that
yeah.
end.
Okay.
Okay, everybody, big
know if you need anything.
Sure, sure.
Okay, I think we're on time here. So now I'd like to bring up the mentor of Tariq, Dr. Sachin Honda.
Thanks, Frank. Thank you all, and thanks to committee for selecting Tariq for this award. So, Tariq joined University of Louisville in 2017, fall 2017. I would say he is the exemplary student I have ever seen during my, graduate school time or postdoc time. So he joined in August, and I see like in August 2017 he came, and then even before classes started, he started doing research work in lab, and which was pretty impressive. And on top of that, I never see any student, who is that punctual. We have in group like every start of week, you need to send your weekly plan by 9 a.m. And I can't find, actually I was checking emails last night, and I couldn't find any email which is actually beyond 9 a.m. So he's really, really punctual in that way. Then we have, by end of every month, you need to send a progress report. And I couldn't find any time, like any day, like any month, he has ever missed. So this was his punctuality. And, for all students sitting here, if you are punctual, you are hardworking, success will come to you, you need to be practical and live in with reality. So Tariq, as I said, like to my group, people say like, we work with a lot of industries, and we got so many awards in terms of funds, and I would always say, all students are behind that, but Tariq is pretty special. His contribution to group was really immense, and that actually helped. His chemistry helped me to bring NSF Career Award. And then we received multiple industrial grants based on his research. So I wish I would have more Tariq, which, who knows? He was everywhere. So he developed, ligand-free catalysis. So people say about sustainability, you need to use earth-abundant metals. You need to use, develop something pretty efficient. And nobody talks about, in practical, how you can achieve something in terms of sustainability. And he has showcased with his work, you can achieve organometallic chemistry without ligands. And also the most benign solvent, which is water in that. And it's not like something, our one speaker one time used word gimmick. You just publish and nobody use your work. His work is pretty useful. And he has solved many problems related to pharmaceutical industries, So you see in literature sometime people use things pretty toxic in the behind to make something green, and that's not really green. So I always say, like, look at when you say green chemistry, is your green chemistry really green? And as I said, he is also very critical. He will criticize his work. He sometimes comes and say, no, this is wrong. We should do in this way. So as I said, my group always miss Tariq, and he will talk about his research work today, about micellar catalysis, and he will talk about, about sustainability and how the work can be much more useful. And I always say, to my wife, I said, I have a prediction, next 10 years, Tariq will be pretty big in the field. So Tariq, I will not waste your time. Come on.
I guess. So, this one. Thank you, Dr. Handa, for the kind introduction, and I'm happy to be here. And I'm really happy that department considered my application, and Dr. Handa supported my application for the PAC award. And it's a great honor to be here. So I'll just give a brief discussion about what I did during my PhD tenure and what I'm currently doing at Millipore Sigma. So I currently work as a scientist at Research and Development at Millipore Sigma, Milwaukee, and I was a grad student with Professor Handa at our department. And the title of my presentation is Palladium Catalysis in Aqueous Micelles. It's sustainable and greener than the earth abundant catalysis. So I'll just briefly discuss. I will not go to the details. I'll just briefly mention how we did chemistry, what is the context of this development, and how we solved it without going to the finer aspects. So before going to anything, this is where I want to start the discussion with, when we consider the evolution of organic synthesis. Organic chemistry is a term that everybody discusses. What is organic chemistry? So it's like the chemistry of carbon and hydrogen when you look at it, like chemistry of molecules of carbon. So it all started with the German chemist Friedrich Wöhler, who synthesized urea in 1828. You can see slowly during the evolution of organic synthesis, you can see the structural complexity of the synthetic target, the molecules, has become more and more complex. And chemists were able to synthesize these complex structures with the development of new reactivities, which is being fueled by new catalytic processes, and also the availability of sophisticated instrumentation techniques like HRMS, mass spec, NMRs to analyze this structure of the molecules also helped. But on the other aspect, when we critically look into this one, each of these synthesis generates enormous amounts of waste. And I will give details in the upcoming slides. What do you mean by this one? And also, when we do this synthesis, it always uses organic solvent as the reaction medium, and often it requires higher temperature and pressures. So more than 80% of waste associated with any organic reaction is derived from the organic solvents. So just to give an understanding, don't worry about the structures. This is just to give an understanding how inefficient is the current organic practices are. So this is Takeda is a pharmaceutical company. This is one of the process for the synthesis of one of the API, TAC 954. So don't look at the details. So it involves multiple steps like cyclization, amidation, deprotection, reductive amination, deprotection, carbamate. So these are all technical things. But just to understand how inefficient these methods is, so this was reported in 2014. So to get a context how inefficient this process is, I'll use a term called process mass intensity, PMI. So PMI is something which discuss about to get 1 kilogram of product, how much ingredients are required. Suppose you want to create a 1 kilo or 1 pound of a material, how much ingredients has to go in. So in this case, in the previous case we have seen, it is 350. That means every 1 kilogram or 2 pounds or 2.5 pounds of the product you are generating you requires 350 kilograms of the ingredients, which means that the current existing technologies are extremely inefficient. And out of that, when they critically analyzed what contributes to this inefficiency, they were come to a conclusion that 75 to 86% of this waste generated is fundamentally the organic solvent. So organic solvent is the reaction medium they use to cook these things up. So organic solvents clearly is the culprit which contributes to the inefficiency of organic processes. So to further understand the environmental impact, you can see this is recently appeared in Chemical Engineering News, where 1,4-dioxane, which is a solvent which has been commonly used for extensively for organic synthesis. This what happens is once it is miscible with water, it is very hard to remove. And what happens is this water contaminated with dioxane goes to the groundwater system and have a significant impact in water supply system. So it affects the well-being of common people. And right now there has been a push for chemical industries to get rid of not using 1,4-dioxane anymore. And similarly, the another commonly used previously was NMP, N-methylpyrrolidine. This also have a health impacts. Similarly, you can see the European REACH is a European organization. They reached an agreement to completely restrict the use of DMF by last year. 2022 was the last year, and there has been serious discussions to completely shut down the use of DMF further. And also there has been potential safety hazards associated with using DMF as a solvent. So all these arising concern on organic solvent, both in terms of environmental as well as health, as well as the worker safety, has been a growing concern in terms of using organic solvents as a reaction medium. So to address this challenge, there were discussions about using water as a reaction medium. You see, organic synthesis has been water, has been emerging. You can see this is for this plot represents number of publications over a period of time for the keyword organic synthesis in water. So here, organic synthesis is carried out in water. So water is the major solvent in using the reactions. So you can see there is a gradual increment in using water as the reaction medium in terms of publications. But there is a major limitation for this method. That is like the water cannot dissolve reactants very well, and the poor solubility of reactants and sensitivity of reactive intermediates or catalyst incompatibility have always caused its adoption at a larger scale. So there has been an interest to use water as a reaction medium, but there is not a proper solution, so because most of the reactants and catalysts are not compatible with the aqueous system. So we wanted to solve this problem. So in recent years, a technology has been developed which is a micellar catalysis, where it employs amphiphilic molecules to carry out organic reactions in aqueous conditions. So how does this work? So this is a key point. So how does this work? For example, consider the amphiphilic molecule PS750M developed in our laboratory. So for example, this molecule has long chain hydrocarbons, and a hydrophilic part consists of a MPEG moiety, which is connected by a linker moiety. So it has a hydrophobic part and a hydrophilic part. Once you put it in water, once you place it in water, these molecules self-aggregate in such a way that hydrophobic moieties comes together and hydrophilic moieties comes together. So they self-aggregate to form a supramolecular structure called micelles, and these micelles, always remember, they have a hydrophobic core and a hydrophilic outside. So this hydrophobic inner core can, once you introduce reactants like organic molecules which are hydrophobic in nature, can go and stay inside this one. So under aqueous conditions, basically these are like reaction pockets where organic molecules can go in, and if there is sufficient reactants are present, they can perform the reaction. So basically you are using water as a bulk reaction medium, no organic solvents are used. You are using very safe water as the reaction medium. So this was our philosophy, to extend this concept and employ this concept across various organic reactions. So in this direction, my whole PhD work was using our laboratory developed PS750M. So this molecule is this is also available in Millipore Sigma via our Aldrich catalog. So this is this is also a business talk. So if you guys ever want to purchase this one, it's available in our company website as well. So apart from this, so if you look at this one, this also have a tertiary amide which is consistent with various polar aprotic solvents, and once it is dissolved in water, you can use the micelles of this one for various organic transformations. So my PhD work leveraged this concept for various organic transformations, which involves like the CN cross couplings, reductive nitroamination, this is a new class of reactions, alpha rylation of nitriles, Suzuki-Miura cross couplings, acid chloride couplings, oxidative Heck couplings, ligand-free catalysis, oxidation chemistry, hydrogenation chemistry, carboxylation of aryl halides, and nucleophilic substitutions. So these are the class of reactions we developed during my tenure using a PS750M as surfactant and under mild aqueous conditions. So I'm not going to talk all of them. I'll be bringing the attention to two important reactions. One is like alpha rylation of nitrile and carboxylation of aryl halides. Why these two projects are important, we will discuss in the coming slides, because both of them have unique role in terms of giving new concept to the scientific audience. So first part will be micelles of PS750M in the context of carboxylation chemistry. So just to understand, going details, carboxylic, what is this carboxylic acid means? Like it's a organic molecules which contains a functional group COOH. So it has been found in wide range of APIs as a molecule as such, or as a precursor to synthesize them. So you can see this is in aspirin you can see a free carboxylic acid, and cloxidine in all kind of the LSC-102, which is recently from Novartis, you can see a free carboxylic acid. So carboxylic acid as such as an important moiety, or carboxylic acid can be modified further to form an amide, which is also another important functional group derived from carboxylic acid, and therefore carboxylic acids are an important class of functional groups which requires extensive, which has an extensive interest from the pharmaceutical industry. So either in the form of salt, acid, amide, ester, or anhydride. This can be all in APIs, it can be existed like that. So traditionally, how organic chemists synthesize these molecules? The easiest way is oxidation, which is very well established classical method like chromium or KMnO4 classical oxidation method, or the most recent one, or everybody loves to use because this technique is so easy, no side reactions from generating from aryl lithium or alkyl lithium or Grignard reagent conjugate with dry ice to generate the carboxylic acid. So these two methods are very classical and has been extensively used so far, but the major problem with both of these methods are it has poor functional group tolerance. What does that mean? Suppose it has like some other groups like aldehydes or ketones or other functional groups, you will have limitation in generating generating the aryl lithium or Grignard reagents, or it will undergo side reactions. Or if you use like oxidizing agents like stoichiometric metallic reagents like KMnO4 or chromium, they are not sustainable. And also most of the time you require like toxic reagent, and the functional group incompatibility is so broad. So what you have to do when you are synthesizing an API, you cannot synthesize carboxylic acid at the end. You have to synthesize always in the beginning, and you have to protect it, which causes a significant issue at the late stage. So introduction of carboxylic group of a functionalized molecule has been always a point of challenge, especially for nitro groups, aldehydes, ketones, nitriles, amides, carbamates, or amines, or Michael acceptors. They are always reactive species and these traditional methods cannot be used. So requires an alternative method, how to develop an alternative solution for this method. So our idea was to use palladium 0 catalysis, palladium 0 to 2 catalysis, which is very well established, which involves 3-step oxidative addition, transmetallation, reductive elimination. These are the 3 basic steps. And our idea was, after the oxidative addition of an electrophile, you introduce a C1 source, transmetallate it, reductively eliminate to give the carboxylate. So we wanted to develop a negative C1 source which could be easily hydrolyzed to give the carboxylate ester. So in this direction, we looked how to develop a C1 source which could easily able to do this one. So idea was chloroform is a very well extensively used solvent. So if you use a base sufficient enough to generate abstract the proton, generates a carbanion which could transmetallate to the oxidatively added species and reductively eliminate this sp2 sp3 species, and if you can in situ hydrolyze, you can get your carboxylate without any problem. So this method does not require any stoichiometric amounts of any metals, no harsh condition. Under aqueous condition, you will be able to generate carboxylic acids which are relevant to pharmaceutical industry or many other chemical industries. So this was our hypothesis. We wanted to test whether this works or not. So in this direction, we screened around 200 experiments to get the right conditions. So from this one, these are some of the experiments which are relevant to talk about. So we took this, so consider this as a Lego piece. So this is a Lego piece which should be replaced with this guy which we wanted to carboxylate. So this is the palladium catalyst we used. We reached it at the using of this the usage of this particular catalyst after screening over 60-70 catalyst catalogs, whatever we have in our kit. So we found that Q-Force palladium crotyl chloride, this was developed by Professor Hardwick. So we used that catalyst technology, tried to merge it with our surfactant chemistry, and we found out that using this catalyst under our micellar conditions, using chloroform as a C1 source, we were able to get the carboxylic acid with 95% of the isolated yield. And any deviation from this conditions, for example, we remove this ligand, only use the palladium source, didn't give the desired product. Replacing the base lithium hydroxide with potassium hydroxide only gave inferior conversion to 73%. Replacing hydroxide base with a weak base didn't give the desired yield. Then we further looked at the base equivalents and other C1 sources similar to chloroform CHBr3, we only observed trace amount of the desired product. And just to showcase how important is the use of surfactant is, you can see when we removed the surfactant and carried out the reaction under water condition, only got 21% of the desired product, which clearly showcase that surfactant is required to run the reaction. And it is interesting to see when we switched this reaction condition, rather than using water as a reaction medium, switched to classical organic solvent, the reaction did not work, only gave not detected very trace amount of the desired products. So with this set of optimized set of conditions, we set out and explored whether these things are compatible with other only applicable to that particular molecule, or can we apply to other molecules. So we screened on a variety of substrate and we showcased our 43 substrate. These are some of the representative examples. You can see this is having an acidic methylene group, did not give any side reaction, gave the desired product. Pyridyl systems, which are normally challenging to do with the traditional route, we were able to carboxylate. Heterocyclic systems which contains carbamates with a cyclopropyl rings, which are very sensitive, were given the product in decent yield. With heterocyclic systems, and we were able to get good yield. And it is important to note that the functional groups like nitro, ketone, nitriles, and nitriles with active methylene groups, which I have previously said that these are problematic substrate, we were able to do the desired transformations on all these molecules with decent yield. And I would like to acknowledge, because this work I got tremendous help from, we had a postdoc, Dr. Susanta Hazra, and recently defended Dr. Sharma. So I would like to acknowledge for their help and contributions in making this project successful. And further this one, we wanted to look into the mechanistic details, because we had a hypothesis, and that hypothesis was like the carbanion route which we discussed. And there is a tremendous possibility that under chloroform with lithium hydroxide or KOH base under aqueous condition, there is a possibility that this could convert to carbon monoxide. And this carbon monoxide could coordinate with palladium, and after the insertion, it can undergo a hydroxycarbonylation pathway to give the carboxylic acid pathway as well. So we wanted to look into the mechanistic details before just claiming that, okay, this is our pathway, that's it. No, we wanted to critically look into what we did, and we critically analyzed it, okay, whether only our hypothesis is operating or a alternative mechanistic pathway is possible. Then we looked into the reaction with carbon monoxide. We took this reaction, we ran reaction under carbon monoxide, we got 49% of the desired product. Then we further looked into the kinetics, how reaction proceeds. If carbon monoxide is generated from chloroform, we should see a similar reaction kinetics. So we didn't see the similar reaction kinetics, which ruled out the extensive operation of the hydroxycarbonylation pathway. And further, we looked into the possibility of using other C1 sources like CHBr3, CHI3 or CHBrCl2. These molecules are much more easier to decompose to give the carbon monoxide, so that if that is being generated, it should give the carboxylic acid as well. In those cases, we did not observe. In the case of chloroform, we only observed the desired product. And further to this one, we wanted to validate using this reaction mechanistic pathway using different tools. So for example, the idea was we will get the aryl bromide, so this is the reaction intermediate we are anticipating, and this reaction intermediate will hydrolyze to give the lithium carboxylate, which we will isolate as the carboxylic acid. So this is what this is the intermediate we are anticipating based on our hypothesis. So we wanted to detect whether it forms or not. So we did a GCMS experiment to see whether we can see or not. So actually this work was done with Dr. Sharma did this work. So because I was graduated and we needed to publish this work, so we looked into the finer details. So here when we looked into, so we took the commercially available CCl3 and injected the sample and see where it comes. So we saw the GC pattern, where it comes. Then if in our reaction, if this CCl3 is being generated, we should be able to at least detect it in a smaller quantities. So we were able to see the detection of this molecule under our reaction conditions, proving that the transient formation of a trichloromethyl species under our reaction condition, giving an indication to what our hypothesis was correct. And further, we also wanted to see, so the first step of what is happening is the chloroform deprotonates, and if we have deuterium source, the CHCl3 will be converted to CDCl3 if we have a D2O source. So we also detected this CDCl3 under GCMS condition. So here you can see the no CDCl3 because this is under PS750M condition with CHCl3. Once we switch it from PS750M H2O to PS750M to D2O, there is a possibility that we should see this one if our hypothesis is correct. We were able to detect the CDCl3 signals, which is consistent with the commercially available sample. So this gives an indication to that our mechanistic hypothesis was correct, and this confirmed our carbanion pathway detected by the GCMS technique. And further, to showcase the application of this methodology, we further looked into the possibility of isotopic labeling of carboxylic acid group. As I have said previously, carboxylic acid groups are very important functional moiety for APIs, and to track them in our body, it is very convenient method is to isotopically label them. So current methods, there is a very few methods which are extremely expensive available to selectively label different atoms in the carboxylic acid group. So what we did was we were able to label 18O oxygens of the carboxylic acid by using 18O water, and we were able to get up to 84.6% of 18O incorporation because there is a competing pathway from lithium hydroxide as well. And similarly, with the use of C13 chloroform, we were able to introduce 13C carbon to the system, and which were very useful from you looking at the application of this methodology. And similarly, we can label both atoms. So this gives a chance to selectively label oxygen atoms or 13C label atoms, or you can label them both. And if you do it in D2O, you can also, rather than by equilibrium, you can have H2D as well. So this will be probably one of the easiest and I would say most convenient and sustainable way to selectively or label multiple atoms in the carboxylic acid group. And further, we took a carboxylic acid, we made a carboxylic acid which contains a ketone, very sensitive functional group. If you use the traditional Grignard route, it will undergo side reactions, and with our methodology we were able to get 63% of the desired product. And with this one, I'll just conclude this part of the project where this application of the carboxylation technology has been used with broad scope. No stoichiometric metallic reductants are used. Sustainable, exploring the reactivity of carbanion type species under water, and it also gives an opportunity to label different atoms, multiple atoms in the carboxylic acid groups, and also we did a extensive work on the mechanistic part as well. So this work was published 2022 November in SCS Catalysis. And next part is, the second part of the presentation is the alpha relation of the alpha relation reactions. Just before going to the finer aspects, I just give a brief background. So the traditional palladium catalysis involves an electrophile and a nucleophile. In terms of using a palladium catalyst, you forms a CC bond. So this electrophile reacts with the nucleophile. So depending upon the name of the nucleophile, you see, for example, you're using a boronic acid or boronate ester, it's called Suzuki-Miura coupling. Or if you're using a zinc reagent as a nucleophile, you're using Negishi coupling. Or if you're using magnesium as the nucleophile, you're doing Kumada coupling. So it basically involves oxidative addition of an electrophile, transmetallation of the nucleophile, reductive elimination, very well established 2010 Nobel Prize work. So if you look into this one, there is a problem, fundamental problem with this approach in terms of step efficiency, because these boronic acids or zinc reagents or Grignard reagents are not readily available. You have to make them. So you will have to take a molecule, do a reaction, isolate or get that solution, then do the next step. So it is step inefficient. So the alpha relation idea is, if you have like organic molecules which has acidic hydrogen, abstract the proton, and this is now a nucleophile. This nucleophile you can couple with an electrophile which is already there and carry out the reaction under the palladium catalytic condition. So this is the concept of alpha relation chemistry, and this has been leveraged for various organic molecules like nitro groups whose pKa is around 10 to 12, nitrile groups 19 to 12, pKa of the amides 20 to 24. So depending upon the fine tuning the base and ligand, it is possible to do CC couplings without using any pre-functionalized starting materials. So this is a powerful tool to construct carbon-carbon bond. So in this direction, we were particularly interested in doing the alpha relation of nitriles, because there has been an interest from a pharmaceutical industry, because it gives an ability, because amide is a functional group, nitrile is a functional group which could be easily converted to various other functional groups like amides or aldehydes or ketones depending upon different conditions. This will be a functional handle to carry out. So in literature, there has been only 4 reports to perform these reactions. The first report came from Miura's group in 1998 with only 3 substrate, and you can see the reaction conditions they used DMF, which we already discussed is a problematic solvent. Also, it requires MS 4 angstrom means it requires extremely anhydrous condition, drying reagents are required. And similarly, in 2002, Hardwick groups reported the application of a BINAP palladium acetate system for a similar reaction. Here you can see they used an extremely strong base, NaHMDS. And also in 2003, Vercade's group reported a new class of ligands for a similar reactions using NaHMDS with a new ligand. And Credence group from Queens reported another methods by which you can effectively have the alpha relation of nitriles. So if you look into all these methods, you can see it requires organic solvent dioxane, requires extremely strong base, higher temperature, strong base, toxic solvents. And common to all this method is the use of organic solvent under extremely anhydrous conditions. Why do we have to use anhydrous conditions? Because we previously saw the previously we saw it involves a carbanion species. So a carbanion species is extremely unstable under aqueous conditions. And when we are in school, it has been taught us, okay, if there is a carbanion, don't use water, use anhydrous condition. That's how we are trained. But this gives an opportunity. So if we wanted to do this reaction, based on the traditional knowledge, this reaction is only possible under anhydrous conditions. But our idea was, can we translate this technology under the micellar condition what we previously proposed, and can we do this reaction or not? So there were challenges in doing this one because the key reaction intermediate is moisture sensitive. So if we want to do this class of reaction, we have to generate the generation of carbanion type reactions in water. So here we came up with a concept. We understood another fundamental nature of how micellar catalysis work. So this is just a cartoon representation of how micellar catalysis works. So this is the catalyst, this is the electrophile, this is the nucleophile. It is floating around. So in presence of a base, this will abstract the proton from here and will generate a carbanion. So under micellar condition, what happens is, previously I have shown the micelle have a hydrophobic inner core. So the reactants are occupied inside there. If the carbanion is generated inside that one, it will be shielded from the exterior water environment. And if there is reactants and catalysts are available with sufficient quantities, it could promote the desired reaction. So this was the idea what we had, and we thought whether this will work or not. So this is basically, we are harnessing the shielding effect of micelles to enable the desired reactivity. So in this direction, we used our nanocatalytic approach using a commercially available exposed palladium chloride system. Here ligated palladium 0 nanoparticles are generated from this parallel system, and generation of nanoparticles were observed with the HRTM analysis. And we initially looked into reaction mechanism, whether it works, how it works or not. So we took the nanoparticles, which is like 43.1 is so we did a phosphorus NMR. So we wanted to see whether the reaction occurs the way we proposed before, like oxidative addition, transmetallation, reductive elimination. So what we did was, we took our catalyst, we took the phosphorus NMR of this one, it comes around 43.1. So this is the reference we used, triphenyl phosphine, which comes around -6.0. With respect to this one, the catalyst comes around 43.1. And once we introduce the aryl bromide and our palladium 0 nanoparticle catalyst, the expected reactivity is the oxidative addition. If it does not undergo any reaction, we should see the signal retained. We didn't see the signal retained. The signal shifted to 60.3, indicating that a possible oxidative addition. Then we wanted to see whether there is a binding of this. So this nitrile will bind to the palladium. Then the base will abstract this proton to generate the palladium bound carbanion. So we looked into this one. We added potassium hydroxide, palladium 0 nanoparticle catalyst, and nitrile. Then we saw the formation of a 3 different set signal. And why this could be possible is because this nitrile can bind to the palladium. Then there will be cis trans geometry will be possible. And also after abstraction of the proton, it will convert to an intermediate called ketone-imminate species, which could be in a cis form or a trans form. So we were anticipating multiple signals, so that also we observed. Then what we did next was, if we get this species, transmethylated species, and we get oxidative species, we mix them together and heat it, we should get back our catalyst back. And we observed the formation of the catalyst back once we did that, giving the indication that the possibility of a oxidative addition, transmetallation, and reductive elimination operation under micellar condition. With this, we further expanded the scope, and over 36 excellent substrates we did, like the scope was really good. And for this work, I wanted to acknowledge 2 postdocs, Dr. Bihani, Dr. Bora, and the French Indian student we had, Dr. Lucy Fink, and also the undergrad, she was high school student that time, Bhavna. So these people contributed in making this project a success. So we had like pyridine systems, CBC system, active methyl systems, indole systems, triazole systems with various substitutions, Indian systems. So we expanded the scope over 36 substrates. Further, we wanted to see whether these molecules whether we can really use this technology at a scale like 50 gram, 100 gram, or more than that. So we just took the reaction, we performed the reaction at a 50 gram scale reaction to generate 50 gram scale reaction to generate the intermediate for this prodrug. And with the reaction worked very clean, no column purification is required, simple crystallization yielded the desired product. Just to give you a context, how clean is the reaction? So this is the desired product. This is the GC analysis or GCMS analysis of the reaction, crude reaction mixture, bromo, nitrile. You can see after 5 hours, this is mostly the product. And after 21 hours, you see very trace amount of aryl bromide, only desired products. This shows that there is normally in organic reactions, always there is a chance of side product formation, especially in this class of reaction. In this case, reaction is very clean, and you don't need a traditional column purification or anything. Just simply after this one, crystallize the product out, And this product, this was featured on the journal cover, and also this was highlighted by various other research groups. For instance, this was Uzumi highlighted our work in SynFact, and it has become a SynFact of the month, and has been also featured in the Chemical Engineering News. So this is the first report where alpha arylation of heteroaryl acetonitriles or these kind of reactions are reported in water, and where we explored the reactivity of carbanion, and we understood the reaction mechanism using different spectroscopic analysis. And with this, like I'll come to a conclusion for my part one of my talk, which is the work, some of the work I did during my PhD tenure. So basically, my whole PhD work was exploring the reactivity of the palladium catalysis in the context of micellar catalytic. So basically, merging these two catalyses to enable various reaction pathways. And also, these are not just like curiosity-driven laboratory scale, small scale reaction. These are easily scalable. And we try to demonstrate in our most of our reactions more than 10, 50, up to 100 gram scale, just to showcase that these are really useful chemistry, and industry is ready to adopt many of these methodologies as well. And I would like to emphasize the carboxylation project, which I discussed in the first part. This is only possible in surfactant chemistry. We tried to do it under organic solvent condition, it does not work. So based on our mechanism, we were able to an extent, give a rationale why it is only work under micellar conditions. And also we try to explore the detailed outline of the reaction mechanisms. And with this part, I am like extremely thankful for the support I got from my research advisor, Professor Sachin Handa. I was like, he has been supportive. He always have a point. Okay, you have to clarify, work on this, improve this. And he always on the top of the things. When you give him a manuscript, okay, ready to submit, he works very quickly, mostly on this time. That's why probably I got 14 to 15 papers during my PhD. During my PhD, because he was very quick in submitting the manuscript and our submitted. Okay, SI is there. Okay, he revised, and he was critical enough. Okay, this is our lacking. We have to work on it. We have to improve on it. And I will be always grateful for shaping and polishing my scientific aptitude and these things. And I'll be always grateful. And I would like to thank my committee members, Professor Nance, Jinjun Lu, and Dr. Fabrice Gallo from Novartis for their supports, comments, and constructive interference at each stage of my graduate studies. And also we have wonderful collaborators, Dr. David Lee, who is right now in Biohaven, who was in Takeda and now transitioned to Biohaven for his, he was like, I would say, one of the most critical person I have seen in my entire life. Whenever we bring in something, he was quick, first of all. Second of all, okay, this is missing, why can't we do this? And he comes up with very good ideas, unlike, like he always found time for us even on Saturdays, Sundays. I'm extremely thankful for him, and Fred, and also Wilfred, and also from our concenter Jasinski for like, I always got walk-in, like whenever I need HRTM analysis or XPS, hey Jasinski, can we do it? I'll just give him a call. Yes, sure, why not? So he always been there for me. I'm always grateful for our collaborators for his help. And also the current lab members, recently defended Dr. Sudharip Sharma, and also Deborah, Gagan, Karanjit Kaur, and the new members of our lab, and also the former members, Dr. Susanta, Dr. Gaspard, and Behrad was an undergrad, Dr. Bihani was a postdoc, Dr. Bora postdoc, Dr. Gade, Justin was my senior, and Uyen, Armand, Lucy, and Bhavna for all their help. And also, of course, my wife is here and for her support, and mom and dad and in-laws and nephews. So now I'll just transition to the work I'm doing right now. I hope I'm not going over time. So I'll just give a brief this one. So I'm part of Millipore Sigma's ChemSynth R&D team. So we are like right now we have on site we have 5 people. So Golin, Yam, it's me. This is Mitch, and Ashish. He's in Bangalore located, and this is our boss Peng, and this is our technology partner. We have collaborative partners. Thomas Colacott, who is very well recognized in the area of palladium catalysis. So right now, I'll just discuss one of the work we recently published. So this is where we did, so this will be a little bit difficult. This may go purely technical. So this is where we use, previously we always saw the coupling of aryl-aryl couplings, sp2-sp2 coupling. So this is a situation where we are looking at the possibility of coupling sp2 systems with sp3 systems. So this is a little bit difficult to do with palladium catalysis, and there is a lack of ligands and catalysts and a general protocol in the, especially in the context of industrial R&D space. So we wanted to develop a catalytic system which can do all kind of sp2 sp3 couplings. So why sp2 sp3 coupling is a little bit difficult? So this is the pathway I previously discussed: oxidative addition, transmetallation, reductive elimination. When it comes to sp2 sp3 couplings, the nucleophile, especially if it is substituted nucleophile, after transmetallation, it can undergo a lot of side reactions. It's like, I will keep it simplified. It can undergo a lot of side reaction, which could be like beta hydride elimination leading to the formation of the isomerized product, or the nucleophile can exchange and give the dehalogenation or homocoupled products. So I will not go to the details, just like keep it simple that in the context of sp2 sp3 coupling, there is always a possibility of lot of side reactions arising from the transmetallation step. So the best ligand right now to do this chemistry is the T-butyl phosphine, DTBPF, developed in 1980s, 1990s. This is the best ligands available commercially to do this class of reaction. So when we correlate this with its bite angle, so bite angle is like once it is coordinated with the metal, you can see there is a 3 points, then you have an angle. So you have larger the angle, so there is a correlation, larger the angle, the better the reactivity, no side reactions. So it all depends on the substitution on the phosphine. More bulkier groups you can put, more bite angles you can have, by that way lesser side reactions you have. So our idea was to introduce much more bulkier group than the T-butyl one, Adamandyl. So this Adamandyl, we wanted to substitute this R group with Adamandyl, then generate a Adamandyl phosphine and generate various tunable systems for the couplings. So in this direction, when we looked at the synthesis of this one, this is a very classical synthesis reported in 1985, and which is very hard to reproduce, to be honest. I tried myself, practically tried to this. It's like the literature report is like around 41% yield. I couldn't even get 5% or 6% yield. And the another method, the Stepniakas groups, this is the one of the most heavily used, the lithiation route quenching with chlorophosphine. And this route is excellent for small phosphines. As soon as you try to introduce phosphines with bulkier groups, this lithiation approach does not work. So bulkier groups like Adamandyl phosphines or other things, you cannot install with this one. For that one, we have to use palladium catalyzed CP couplings. So we developed a palladium catalyzed CP coupling route to make this ligand with very minimal palladium to do this reaction. So further, so this is where we are looking at a different nucleophiles, so electrophile nucleophile. This is like Grignard reagent, if it is a lithium, Murahashi-Faringa type coupling, Negishi coupling or Suzuki couplings, if it is boronic acid. We tried to do all these reactions, and we were able to get, we used a simple N-butyl substituted nucleophile with lithium, magnesium, zinc or boronic acid. We were able to obtain reaction yield with 86 to 95. Our attempt was to develop a catalyst which could able to do all these kind of catalysts. So we were able to do this one, and we wanted to showcase its application in installing the cyclopropyl group, because cyclopropyl group has a huge application in the context of pharmaceutical industry. For example, these are the two drugs where you can see the installation of the presence of cyclopropyl groups are there. So introduction of cyclopropyl groups is important, and we are developing a catalyst which could be able to do this reaction, and we were able to do this reaction with decent yield ranging from 79 to 90. Further, we also able to showcase, okay, this works on chloro and bromo systems. Chloro is a little bit challenging, so we were able to achieve all these transformations, and also Merck's informal library type molecules, we were able to functionalize it. And further, we have to be totally honest, this is not a universal catalyst, magical catalyst which works for everything. No, this does not work. When I bring the substituted nucleophiles like sec-butyl group, it's good. It gives 85, 86, 95, 72. And it always have a branched to linear ratio. So I told you previously about the possibility of side reaction. It can give side reaction at this site, secondary site, or primary site or a secondary site. It always gives a mixture of product, except when we are using the boronic acid. So whenever we are using zinc, magnesium or lithium, we always get substantial amount of isomerization. And when it comes to little bit more sterically challenging group, it does not work. And when it comes to the tertiary group, it does not work at all. Whatever products we get, it is isomerized product. Only the isomerized product is able to observe. We were not able to install T-butyl groups under this condition, this one. So in this direction, we worked on a new development of a new catalyst. We just submitted the patent. Which is capable of enabling this class of coupling, and this will be commercially available soon, probably by end of this year. So to give a summary, we developed a novel class of substituted electron-rich bulky ligands capable of enabling sp2, sp3 couplings for a broad range of nucleophiles, and we are working towards in developing new catalytic technologies which could solve the existing problems. And with this, I would like to thank the audience. Thank you for your attention. I'll be happy to answer any questions if you guys have.
Okay. Eric will take some questions. If anybody has any?
You are using their ferrocene complex ligands, right? Why not viral ligands, GFOS, something like that?
So this is have to be what I would say. That is a licensing issue, I would say. Ferrocene is not licensed by or not patented by anybody. It's a common commodity. Anybody can functionalize. But when it goes to the bi-aryl core, it is mostly patented or covered in the patents of Buchwald. So it is very hard to get a non-licensed substitution product from the bi-aryl core because it's mostly covered. Whether they made it or not, it's already covered by the Buchwald's patents. So as a company, we always want to make money. So we wanted to make molecules which are not patent burdened by someone else. We have to have our own cores. So that's the reason why we look for the cores which are not like covered by anyone's patent. So that's the reason why we stick to cores which are like open.
I have a question. So you talked about sustainability, what you did here. You can do that chemistry in water. Is it because of, again, patent issue? Because
Translating
the making ligand, you are doing again in toluene.
so
And if you can push sustainability doing in water, but I don't understand, is it because company have to pay someone else for that, or they can't patent the process? Where is the problem?
if we want to develop a new core, new ligand, we cannot use a core which is patented by someone.
So you are using organic solvents to synthesize these ligands.
Yes.
You can use boronic acid and then do the cross coupling in water.
So
So is it due to because they have to pay?
there are 3, I would say, good publications will be coming shortly, which will be dealing with the sustainable synthesis of ligands, which are commercially available with the sustainable technologies. Yes, we have. We are that one.
When you were going through the mechanism and showed that you made the trimethylfluoro, I wasn't looking quickly enough because I didn't think about this. What's the slow step in that overall thing? The hydrolysis?
Now,
The trichloromethyl or making it?
I would say making it will be harder because
But
it should be like a transient enough to detect it, because if CCl3 is formed, hydrolysis, based on our understanding, hydrolysis should be much faster.
why, I mean, is that always true? So you don't need catalysis, you just mix anything with the trichloromethyl group with water and it hydrolyzes?
So CCl3, what we did, so you talk.
I'm just used to chloroform, that's the only trichloromethyl I'm used to, and that of course does not.
No. So it should be like a quaternary center with 3 halogen atoms are unstable. You use hydroxide and base, it will hydrolyze to give the, first it will generate the acid chloride, on the second one replace, it will give the
But that's pretty high concentrations in the base, right?
Yeah, it's probably 6
Okay, so then how can you say that, oh, it's just water? Right, you're gonna have to treat that highly basic solution the same way you would redistill organic solvent to recapture it.
So
For your sustainability and your calculation, you will have to, I mean, that's not just water now, it's like high concentration hydroxide, right?
yeah, we are using hydroxide. So I agree with you on that part, but the sustainability is in other aspect with using organic solvent is ultimately all the organic solvents you have to burn, which will generate carbon dioxide, and that, so every company nowadays wants to bring down their carbon footprints. So switching from organic solvent to a water system, you are like reducing your carbon footprint drastically. So that is the reason why there is a push to use alternative solvents, rather than not carbon based, other solvents to use this one. So in that context, yes, water has advantage, but like you discussed, in using excessive amount of base and water, it has corrosive effect and other non-sustainability features
People
as well.
build membranes now to do this, dealing with this problem already.
Oh.
So yeah, it's very easy. There is a literature. Please, cool and clean water
Come on.
with membranes.
Sure, yeah, I want to ask you that the classic carboxylation reaction that you showed, you know if there is a reason why they're using such a high valence nickel oxide there? It's chromium 6.
Because I believe if you are converting like because always there is, for any oxidation, it's all depends upon the switching between the oxidation state, how it is feasible, right? So chromium or manganese, all these have in that space in terms of switching the oxidation states are much more easier. That could be the reason why they're relying on manganese 7.
All right. Okay. I would have thought, maybe somewhere intermediate, chromium 3, for example, would have been at 4 rather than chromium 6 seems kind of extreme.
But it has to come down from, if you are oxidizing another species, one species has to go to reduce, right? So you start from a higher oxidation, one comes to lower oxidation, this goes to higher oxidation.
You can do a 3 electron transfer to the chromium 3, which is the more stable one.
I am not sure on that.
I have one question for you. I think I should ask you. So you use base, back to Professor Mueller's question. What if you use electron, just electric current to generate carbonate? You don't use any base anymore. You generate hydrogen.
That will be,
So single electron or dual electron transfer from fluoroform, and then what you generate as a wasted hydrogen gas. And
that-
then you deal with this problem, and I think I discussed with one of student this also.
that-
Do you
that-
think like ligand will play important role in that? Because this ligand, the bite angle wise, I don't think you need to bring that on the palladium CH agnostic first, then this electrochemistry can happen. So do you think it can happen?
it can happen. Probably the best route will be switching to nickel, from palladium to nickel.
Okay.
That will be much more.
So you were talking about sustainability in terms of the solvent and the synthesis, but what about the separation of the products?
So
And the purification workup, I guess.
yeah, there was like two parts for this question. So first part is like, how do we still isolate the product? Are we using organic solvent? If you are using organic solvent, are we still going to do the traditional purification, or there is alternative methods? So on the alternative method sides, there are people's are right now, like there are paper published from our group itself, like where you can do couplings, product just crashes out, filter it. In that case, that is the most ideal scenario where you put the reaction, the product crashes out, filter out. So Sudhir's couple of amide papers are there, we did that one. In those cases, completely organic solvent free, you don't have to touch organic solvent. But these examples I've shown, like not in the carboxylation case, but the nitrile case, we have to use the traditional, we have to use organic solvent to extract.
Which solvent you use?
We use ethyl acetate,
Is
which
it
is,
green and
it's
compared
greener.
to or not?
It is much greener compared to we use like a greener solvent to extract the product out, and we try to use a minimal solvent. So when we calculate the total, I would say we call the factor is called E factor. So how much waste will be generated compared to a classical process, even though with the use of organic solvent to extract the product, this comes lower than using the traditional approach.
So whole idea is to not use dioxane, DMF and all that.
Yeah, I was gonna ask similar.
My question, it doesn't have anything to do with the chemistry, though, it's more of a business question. Obviously, Millipore, well, some of the compounds you work with, some of this information that you learn, you would keep as a trade secret.
Yes.
And some other information you share in journals with the public. How do you choose what to share and what to keep as a trade secret?
So, the best way we do is like the processes, the way we synthesize the molecules, we don't give out by any means. We don't even go for patents for processes, because there are countries which don't care about process patents. They just take the process, they do it there, then they violate, because there are instances where we are right now dealing is people tell they shipped, I think, benzoxazole, which is like a common chemical, but when you look into that one, it's not actually a benzoxazole, it's one of the process patented material, and people are suing each other. You cannot ship the material because when you are shipping, you cannot, if you are made in a patent a country which does not follow the patent, and you are shipping to US, you cannot ship it like that. And what the companies does is they say, oh, we are not shipping, we are shipping a benzoxazole, and they give all paperwork for the benzoxazole. Customs clears it, no patent, nothing. This one, and if you are very unlucky, sometime it get caught. For like this benzoxazole incident, they get caught. This is someone else's molecule, then there is a sue happens. So what we does is, by any means, we will not publish the process or procedures by which we make molecules. And we advertise the final products mostly, because publication is a very great way to advertise what we do, what we make, what are our new products available. So scientific community knows, oh, okay, they have this material in their portfolio. So it's basically, publication is mostly as a support system for the marketing,
Okay,
along with the scientific endeavor.
thank you.
Yeah, getting back to the sustainability and green issues, so, like many people said, you can have other reactants in the water, or you have to do separations. I imagine you have to purify water, like that
Yes.
costs energy, right? Mining the palladium and your catalyst, synthesizing the micelle, I mean, how do you, all those are gonna take normal energy sources, right? Carbon-based fuels to synthesize or do these steps. How do you decide when, even water, I don't think you can just say water is green, right, in all cases, so.
Yeah,
How does someone decide, wow, this is a really big impact paper, or this is really a big impact process?
so there is I always have the somewhat concerns of this part has been reported by one of our collaborator, Fabrice, reported in OPRD. This water chemistry is not the ultimate solution for things, but he says that this will be one of the right steps to take right now in changing things to I would say a better direction, rather than depending upon the old school technology. And also he mentions that in surfactant chemistry there are challenges. How do we synthesize the surfactant? Are we still using the organic solvent method, or we are just taking from nature one compound doing it? And we recently wrote a nice coordination chemistry review article just highlighting these challenges as well. And also there is an issue like after these reactions, how do we remove surfactants from the water? That's also
also
useful.
trade secret for our surfactant. We didn't publish. The trade secret we also kept.
So those things are still needs to be addressed. I have the same concerns that you share.
I
How many
would
times
say-
can you reuse a solution of your micelle?
At least 5 times so far. We have palladium catalyzed conducts. We did at least 5 times you can recycle without using significant activity if it involves a palladium system. If it does not,
So if you do it 5 times, what's roughly the mass of product versus the mass of total micelle?
so we
All
use
micelles?
2 weight percent or 3 weight percent is the optimal one we use. So for like every 100 ml we use like 3 grams.
Then that's by micelle or by palladium?
No, by surfactant, just the micelle, the surfactant molecules.
It's a minimal.
Very minimal we can do.
So you should actually say, to be honest with you, nothing in synthetic lab is green. If anyone saying I do green chemistry, it's a fake.
Ultimate green
You can
chemistry
say
is different.
better, nothing is green, only nature is green. That's what I always say.
Just one more question. I'm thinking about, you're doing this reaction with micelles versus the traditional organic solvent. You can probably dissolve much more reagents in the organic solvent and get a much higher throughput of products than you can with the micelles. So are you running into a competition of how much product you can produce in the traditional case versus this
Yeah,
green technology?
that's a good point. Like like as we discussed, Fabrice Gallo is one of our collaborators. He extensively run and compared actually the output from a particular volume with respect to organic solvent and also from the micellar catalysis conditions. So he published, I think it is in 2015.
They have a recent actually, they compared actually, they micellar versus that, it's a $1.8 million saving in one batch, plus environmental saving. So when you are saying you can dissolve so much, and then when you dissolve so much, then you can't control the kinetics. So you are giving offer for side reactions. So you are losing yields. So then the separation is difficult, and that's another problem how you face.
There are two good relevant, just to add to this one, there are 2 relevant articles. One is published in 2015, Green Chemistry by Fabrice Gallo, which exclusively discusses the synthesis of a full-scale API in scale, like multi-kilograms, which compares head-to-head with the surfactant chemistry and the traditional chemistry. And by all means, in terms of environmental impact or PMIs or cost, this is far better. And there is a recent OPRD they update, like they gave for the synthesis of another class of APIs, which is different from what he published in 2015, where also surfactant chemistry is like far superior compared to the traditional organic synthesis.
And that will hold for fine chemicals? Do you think it will ever hold for bulk chemicals?
That space is different.
Yeah, no, that's what I'm asking.
Yeah, that probably have to have a exhaustive studies should be in that direction to make like okay, this is better to make such a comment, but it will be hopeful based on these results. It will be promising in that direction as well, I guess.
Tariq, one general question. Where is the gap, you now working in industry, where is the gap, people publish so many papers, so much good science come out every day, but when it comes to the usefulness, we are still relying on outdated chemistry or in a bulk. Where you think is that gap? You feel like there is something wrong, as a student, from student to when you went to industry, you think like this could be in our curriculum or this, where you feel like that?
I would say it all depends on the investments. I would say like the previous infrastructure has been invested so much on previous chemistry. So when I joined Millipore Sigma, I got like a 2 months training just to how to set up basic reactions the way they do. So everything is like they invested so much in for a what I would say for the traditional setup. So to incorporate, suppose you want to change something, you have to start for a paperwork which takes probably like 1 year, 6 to 7 months just to complete that one. So investment has been so much happened for the old generation, and to push that thing and update it with something new, it's.
But how you will deal with that? There will be always a wall, and that wall is always big when you try to remove that outdated or old-fashioned things. So in industry, can you do by as a
So
you have freedom?
So right now, like if anything which saves money for the company, they will do it.
Okay.
So we have to come up with a justification that yeah, for long run this saves money. Oh yeah, we will invest.
So it's not greener, it's then more economical.
Economical.
It is green, the dollar. Yes,
well, I think if there's no more questions, I think there's still some food upstairs, so we can ask parents a few questions there, but let's thank again the 2022 George Pack Award winners.
Hey, you're very impressive.
Thank you.
Just say one more thing, just again, just one more thing. Quick, if you didn't get a brochure, maybe grab a brochure. Also, there's a giving link on there, so if you want to, if you feel inspired by this George Pack Award ceremony and you want to give to the fund, there's a site on there that you can go on there and give directly over the website. And again, just want to thank the family, some of the family members of George Pack, and again, all of you for attending. And again, congratulate Eric again. Thank you.
I just want to say, I'm a member of Mensa, so I do hang out with Lois.
I have to run to the
Good
airport.
thing, Bob. Yeah, hope we didn't go too long there for you.
No,
You're
it's
gonna be able to
good.
make it in
I
time.
enjoyed it.